So where were we? So we were. So the last thing that we did is we looked at operational semantics, right? And we said, in particular, we looked at small step operational semantics. We said small step operational semantics sort of gives you a way to describe what happens in exactly one step, right? So it doesn't tell you about the result of the evaluation. It says what happens for one step. And what we want to do is to do the same thing as what we did for big step semantics, is to encode them as an inductive type. Inductive because this is an program. This is the language that we are describing will not terminate, right? So that may not terminate. So that's why we are describing. We will describe it as a inductive type. So here is the inductive type definition that corresponds to. Do it this way. Keep it full screen inside. Here's the inductive type definition that corresponds to the small step semantics. Make it a little bit bigger. Okay. So yeah, so we have an assignment step first, and okay. So what is the structure, right? So the structure of the small step semantics is it relates a valuation command to a valuation command. The state in this transition system, if you might call it that, is a valuation command. So every step is going to have the same kind of a state, a valuation command, and goes to valuation command. So the small step semantics itself is defined as a relation that relates a pair of valuation and a command to another pair of valuation and a command, right? And the actual definitions are direct translations of what you find here. So I have a let's look at assignment, right? Valuation command, where the command is assignment. You go to a new valuation where you extend the valuation with the result of interpreting E in V for X, and then the command becomes skip. So step assign is that rule. It says you can step from any valuation to with the command assignment of X to E to this state, right? This configuration where the command is now skipped and the valuation has been extended with um, X bound to whatever the result of interpreting E in V is, right? So that's assignment. Let's maybe look at one other thing. Maybe we can do. Let's do sequencing, right? So sequencing is interesting because it exactly tells you one step, and if you sort of stare at sequencing, this will come up in the proofs as well. So observe that in all of the rules except sequencing, the arrow sort of only appears on the bottom, right? It doesn't appear on the top. But this is sort of a recursive rule. So in order to show something about taking a step in the sequencing command, you have to sort of explain what happens for taking a step in C1, right? So this will sort of inform. This is the reason why we will see we will treat the sequencing a little bit differently when it comes to proof, because this hides an inductive structure underneath, and everything else is sort of straightforward. This is the only one that sort of has an inductive property. Let's look at that, right? So it says V C1 semicolon C2 is related to V prime C1 prime semicolon C2. Oops. So here is that sequencing, right? So yeah, so V C1 semicolon C2, right, is related to V prime C1 prime semicolon C2 if you can relate V C1 to V prime C1 prime, right? If you can take a step from V C1 to V prime C1 prime. So this is the interesting step, right? This is the only one that has a step on the antecedent as well. Everything else does not have the step relation on the antecedent. Only in the bottom of the arrow does it appear. Okay, everything else is just a straightforward translation. So I recommend you to go through it in your own time, but it's just a straightforward translation. So the way we can, so one thing to now do is, so we've defined what happens for a particular step, right? And how do we talk about executions of programs? So we don't want to talk about, say, one step at a time. Oh, you take this factorial program, the next step will be this one, right? So how do you give semantics for the entire program execution? Here in the big step semantics, we were able to give semantics for what is the result when the program finishes execution, because that is how we define the semantics, right? So in the big step, it tells you precisely what happens when the program completes evaluation, what the valuation will be. Here we have to use something else. This is only describing a single step. But thankfully, we've seen some of the infrastructure already. So we define this transfer flexive closure, which is take a relation, binary relation, right? And then you define a transfer flexive closure of that binary relation by saying TRC is defined if it relates the state to the same state, as well as you can take one step and then again TRC, right? That's the um, that's the transitive step. So precisely we are going to use that, right? So we are going to give semantics for program. Say I'm going to talk about factorial and its output, right? By using transitive flexive closure on this relation. So step relation is defined this way precisely because it relates some state S to some state S prime, right? And just to recall, so if you check TRC, right? Um, so TRC is a relation that sort of relates. Let's print it so that we can actually see the details. So TRC is itself an inductive type, right? And it is taking some relation which relates A, and it gives you the transfer flexive closure of that relation. So it is defined by reflexivity, right? So you relate two states. The state is related to itself in this transfer flexive closure, and this front rule. It says you can take a step from. So if R is related to, if X is related to R, right? And Y is related to Z by transfer flexive closure, then X is related to Z. And the particular instantiation here is that we are going to use it on the step function. So the way to read this is, um, so the current state in the small step semantics is related to itself in transfer flexive closure, right? And this TRC front rule translates to, you can, if you can take a step from X to Y and you can take multiple steps from Y to Z, then you can take multiple steps from X to Z. This is precisely what the reading of this TRC instantiated with the step relation is going to give you. And we are going to use that, right? And the way we sort of read this is, you start with, so what is StepStar giving you, right? You start um, with this state, right? And the state is going to be a pair of valuation, and the valuation is going to have exactly one binding where input is 2, and you run the factorial program. By running, we just mean apply multiple steps of factorial, right? Until you eventually get to skip. So the program has finished termination, right? So the command is skip, so the program has terminated. So what we say at that point, so let's call it V. I mean, it's an existential variable here because we have to show for that V. We show that if you look up output variable in that, it will be sum2, right? So we are sort of using what we learned uh, in the transition system lecture. We are using that in practice here, right? So how do we actually go about and prove this? We are not going to use. So even though this gives you a transition system, and you can come up with inductive properties, right? Um, Inductive invariance to actually prove properties here. We are going to do the direct proof, right? So just so that we understand what is happening and how to apply the proof steps. Okay, so this is what we want to show. How do you prove it? We have an existential and we have a conjunction. So EX is propositional. So and that brings in a unification variable and then breaks it up into two. Let's look at what the factorial definition is. So factorial is a definition, so I unfold it. This unfolds it in place, right? Now, how do I apply these steps? This is similar to what we have seen in the transition system lecture. So I have a TRC here, transitive reflexive closure. There are two possible ways you can unfold it, right? You can either unfold it as the same state relating to itself, or this transitive step, which says take one step, take many steps, then it is related, right? So I'm calling E constructor here. So there are two constructors, right? There is the reflexivity TRC refill constructor and the TRC, what was the other one called? Let's find that one. So one is called TRC refill and the other one is called TRC front. So TRC refill sort of relates X to itself, right? And let's see whether that can be applied. That cannot be applied here because if you sort of stare at this one, TRC refill only holds when the term here is the same as the term here. It may have unification variables, but in particular the command here, right, is different from skip. So TRC refill does not apply. So what applies when you call E constructor here is it unifies with the TRC step, right? And TRC front, and TRC front itself has two subgoals, right? It says, tell me how to take one step, and then tell me how to take multiple steps, and then I will sort of take that as the proof for this one, right? So when I apply E constructor here, right, I'm going to get two subgoals, one for the actual step and another for the rest of the transitive steps. So that's why I get one where I just get a plain step, right? Another where it says, okay, you can take a plain step, go to some y, right? And from this question mark y, you can take multiple steps and go to skip, right? And you get some valuation. I'm going to tell you something about the valuation, right? This is going to repeat itself. So this pattern is going to repeat itself for every step of the way. So now this is sort of plain old application of the corresponding constructor, right? So here we have a sequencing, right? I first assign output to one, and then I have the while command. So when I call E constructor, I'm going to apply sequencing. Sequencing sort of breaks it up into two steps for the first command and the second command, right? I have the first command, which is the assignment. So when I call E constructor, I'm going to apply the assignment rule. When I apply the assignment rule, that sort of plugs in the rest of the variables, right? So the only thing to notice is that the effect of assignment is going to be reflected in the valuation, right? So the valuation here is going to be just empty valuation with input 2. And if I extend it, the way to read this is it is actually explicitly writing down the interpretation function. It is not simplifying it. But if you simplify it at this point, you see that the effect of this assignment has been reflected in the valuation. And then the command itself has transformed to skip because you executed one step. This is skip because C1 was in fact assignment for which you got a skip, and C1 prime is a skip. So C1 prime is a skip here. And that's why we ended up in this state where the command itself is a skip and we have a while that is left over, right? And we are back to square one. So we are sort of in this step star state. You have to do the same thing again, right? So this is going to repeat itself. So one more application to do one step of the evaluation, right? And then followed by multiple steps. And here, if I just apply E constructor, it will pick the wrong, it will unify with this term, right? And it will say, give me a way to go from V comma skip to something else that is not defined in the semantics, right? Actually, you have to pick the right rule to apply. We have to pick this one to apply because if you stare at this is skip semicolon some command, right? And the rule to apply is this one, which is called, we have two step functions. So first one is this step seek 1, and second one is step seek 2. And this is what we want, right? Step seek 2 says that if you have a skip semicolon C2, then you can step from that to just C2. And this is the reason why I explicitly applied this one here. And the effect of doing that is just that the skip is thrown away and the rest of the things are unified and you are back to square one, where you just evaluated output. I mean, it's a bit tedious, but that's precisely what is going on here. I mean, all you have to do is very similar to what we did for big step semantics, except that we also have to break apart this transitive reflexive closure at each step. I recommend you to go through the rest of it in your own time, right? So if you keep doing this, you will build this big term, and you simplify it. This will lead to precisely what you expect. So this goes through. You can tediously do it, but as we studied in the logic programming lecture, you can sort of automate this, right? So just like how we automated this for big step semantics, so what all have we done, right? We applied there is a possible application of TRC refill, but most of the time we apply TRC front, and then one of these rules apply, right? One of the structural rules of small step semantics, which is assignment step seek 2, step seek 1. If true, then you have to simplify inequality. You can sort of go through it step by step. So this is sort of written down based on what we've done here, and that explains how to take one step. And we define this tactic called stepper, which simplifies, tries equality, if not repeats step 1, right? And one of this will go through. So that's similar to what we have defined earlier with the evaluator, right? We had defined evaluate somewhere. Yeah, this evaluate tactic, right? We are doing the same thing here. We just call it stepper tactic. And what is the advantage of doing that stepper tactic? And you can essentially do away with all of the tedium. So we had lots of tedious steps here, and all of that is sort of squirreled away into these stepper functions. We do EX is propositional, but 2 applications of stepper will make it go through. Takes a while, but anyway. So yeah, so the high level takeaway is that we have small step semantics, and the way we describe giving semantics for programs is that we sort of consider that as repeated applications of the small step semantics, right? And in this case, we are in fact talking about a particular terminating program. So this is the terminating condition, right? So when the rule comes to skip, there is no other transition that is possible from here. But it might be possible that if you write a wrong program, you will never reach the state. I'm saying I will reach the state, but if you just write an infinite loop, you will get stuck trying to prove this. You will never be able to show that you can reach the state, which is what will happen if you write an infinite program. We are reasoning about a finite program here. Okay? Anyway, so that is what I wanted to say. And the thing that you can already observe is that these two semantics are equivalent. The big step and the small step semantics. They are just 2 ways of giving semantics. Of course, there are differences, right? One can explain things about terminating programs. Only terminating programs. One can give semantics for non-terminating programs as well. But we can relate them with in both ways, right? Big step semantics is related to small step and small step to big step. So we are going to prove these theorems, and I'm going to give you, and I'm going to step through this. The reason I'm going to step through this is because in the assignment that accompanies operational semantics this lecture, you will be asked to, you will be given a small language for which you have to describe the semantics, right? And it will have non-determinism in that language. And the question will ask you to relate big and small step semantics in certain way, right? It's an interesting language, so it won't be exactly the same, but you'll have to organize your proof in similar lemmas and theorems, right? So it's that's the reason why I'm going to go through this in detail. At a high level, right? Um, what we have is this is how you relate big step to small step semantics, which is that let's say you have an initial valuation v and c prime, and you have a final valuation v prime. Why is it called initial and final? If you big step evaluate v comma c to v prime, right, then it is the same as um, having an initial configuration which is v comma c, applying repeated applications of small step semantics, right, step star, until you get to a skip, right? And when you get to a skip, the program is done. So you're sort of only telling something about the case when the program has actually terminated, right? Because eval is a big step semantics, and that only explains something about the terminated programs. And here we are saying when the program execution terminates in small step semantics, the evaluation is going to be the same v prime, right? So that is what we are relating. So for the particular semantics that we've defined, right, we have the same language. We gave both the big step semantics and small step semantics. And what we're saying is that our definition of big step semantics and small step semantics, correspondingly eval and step, are related by this theorem, right? And similarly, we are going to also see the other way around. Again, we are talking about the terminating programs here, right? So I'm taking, so this goes the other way. So it says that you start with the v comma c, right? And you apply multiple iterations of small step semantics. You take multiple steps. Eventually, when you end up with skip, right? If the valuation is v prime, then if you big step evaluate vc, then you will also end up with the same v prime, right? There are 2 points to remember here. By writing the definition this way, I'm only talking about the program that terminates, right? This is sort of a terminating state, the final state for this one, but the program itself might not terminate here, right? And these are talking about a specific big step and small step semantics, right? Um, these are inductive types. Of course, you can give different semantics for big step and small step, and you won't be able to prove that equivalence. What we are saying is that for our definition, which we think is the same semantics for both big step and small step, we are in fact showing that that is in fact the case. Okay, so how do we actually prove this? So let's do the first one first. So this first one is relating big step semantics to small step semantics evaluation, right? So the thing, as I mentioned earlier, is that there is something special about this this rule, right? The step one rule, because it's the only one that sort of has this inductive structure. Everything else does not have the arrow on the antecedent, but this is the only one that has. So we have to describe a separate lemma. It sort of says something very standard, right? Let's read the lemma first. So if I can take multiple steps, right, with starting from the valuation v in c1 semicolon c2, and I end up with v prime. If I can, I mean, I will end up with v prime c1 prime c2 if it can be shown that I can take multiple steps, right, with vc1 to v prime c1 prime, right? So to v prime c1 prime. So c1 prime is here, v prime is here. All it is saying is that the step rule itself, right? The step rule itself says what is the meaning of taking a single step in C1. This rule is sort of saying what is the meaning of multiple steps in in the sequence where you have C1 semicolon C2 in C1 is can be shown if you can show that you can take multiple steps just in C1. Right? So the only difference is that we have an inductive definition. The seek step one inductive definition talks about relates step and step, here we have step star, right? So that's the only thing that we are adding here. So we intuitively think this is true. So let's actually go ahead and prove it. So I'm actually using induct one here. The way to read this is that because step star this is an inductive type, this is a transitive reflexive closure, right? I'm inductive on the structure of the transitive reflexive closure. So there are two constructors, right? So the reflexivity case and transitivity case, which is what we will get as a result of this. And everything else is just unification variable. So you can directly induct on one. You get two cases, which corresponds to the reflexive case, right? One is the reflexive case. So you see that this is the same as these two states are the same. That's because we are applying the reflexive constructor. And the second one is the transitive case, which we will come back to. So the reflexivity directly goes through, right? So because step star, so we have TRC refl, which relates for any relation given state to itself, right? So the constructor just makes it true. For the other case, it produces the induction hypothesis as well, right? That is there. So let's see what we have in hand, right? It says that, actually, let's do one thing first. So let's just focus on this H hypothesis, right? It says I am going to step from VC1 to some Y, right? But we know that step function itself is going to relate a pair of V comma C1 to some V prime comma C1 prime. So this Y is a pair of valuation and command, right? And Y is some variable that Coq has introduced. But if you do cases Y or destruct Y, all you're saying is that Coq, can you concretize the fact that Y is in fact a pair, right? I'm using cases Y, but you can also destruct Y here. All you're doing is that there is a single case for Y, and the only case is the pair constructor. And that is what Coq does. It sort of replaces Y with V0 comma C. It just came up with these variables, right? And now we can sort of read intuitively what we have, right? So in the hypothesis, we have V1, right? Sorry, VC1, and it says that you can take a step from VC1 to V0C0, right? And you can take multiple steps from V0C to V prime C1 prime, right? And I want to show that I can go from C1 C2 to C1 prime C2, right? C1 prime is here, right? We got from C1 to C1 prime here, right? Through this intermediate step V0C0 V0C. But we also have the induction hypothesis that sort of relates on every C2, right? For all C2, it is going to relate how to sort of plug this in. So I have this fact, right, which is sort of only talking about C1. C2 does not appear here, right? But this induction hypothesis, I mean, you can look at the detail, but what it's saying is that how do I plug in this fact into this sequencing command, right, is what the induction hypothesis is giving us. Let's actually prove it step by step, right? So first thing we want to do is to apply, so these are not equal states, right? So we have to go through one step and then a sequence of transitive steps. So this is going to apply TRC front constructor. So I'm going to take one step here. Okay. How do I take that step? You can apply constructor here, right? Which essentially says for arbitrary C1, C2, because I know I can take a C1, I can take a step from C1 to C. It must be the fact that this is step seq1, and that is a constructor that is applied there, right? So it says, tell me how to step from C1 to some C1 prime, right? And this is part of the assumption, right? This is part of the assumption. We know what the result of stepping from VC1 is, and that's V0C, and these are unification variables. So E assumption will satisfy that. And here is the tricky bit. I mean, it looks complicated, but really, this is the place where you apply induction hypothesis. So let's just stare at it for a minute, right? So C2 is a free variable here. C2 comes from here, right? We have C2 here, we have C2 here, we have C2 here, we have C2 here, right? This variable C1 prime 0 and V prime 0 are actually for all quantified variable, right? C1 prime 0, V prime 0, right? And similarly, we have the variables VC1 here, right? And they are also quantified here. And the only variables that are free here are V0 and C. And in fact, we actually have a equality here, right? Wherever we say that V0 is equal to V and C is equal to C1. So essentially what we are going to do is to plug this fact in. We are going to apply the induction hypothesis, and we are going to get obvious looking goals to prove, right? But the reason why we can apply this induction hypothesis is because even though these variables are not are just different names, they're all universally quantified ones, so we can apply the induction hypothesis. So we apply induction hypothesis here. We are obligated to show that I mean, we plugged it in, so it turned out that we have one goal for this one, and V and C1 got unified with V0C there. So we are expected to show that V0C equals V0C, which is true, which is equality, right? And similarly for the next one as well. Okay, so it was a bit tedious, but the structure of that is important because you will have to do the same thing in your assignment as well. But once you see what is going on, it's there isn't much going on there. It's just a proper application of the induction hypothesis at a given time. The assignment will sort of follow a similar structure, right? So the proof will have to follow the similar structure. So it is useful to study what is going on here. What have we proved, right? We proved this obvious fact that if you can take multiple steps from C1 to C1 prime, where the valuation goes from V to V prime, then you can use that in this sequence command as well, right? Where you have a sequence C1, C2, you can go from C1, C2 to C1 prime C2, where the valuation goes from V to V to V prime. Okay, that's done. So, and then we can now directly go on to prove the theorem that relates big to small step semantics, right? Again, the interesting bit is we are actually inducting on the big step evaluation. Because that's an inductor, we are going to get one step for each of the possible big step evaluation steps. And for each of those, we have to show that small step semantics is also related, right? And big step is sort of recursively defined, so we get the induction hypothesis as well. So we'll come to that. But the first thing that we do is we actually perform induction on the derivation, on the definition of this big step semantics. We simplify, right? And the small step semantics leaves us with the 7 goals that correspond to the 7 rules in the big step semantics. So the first one says that you can take 0 or more steps and go from V skip to V skip. This is true, right? Even though we cannot step from V skip, this is a transitive reflexive closure. These two states are related by reflexivity, right? So that is what we are appealing here. So we are applying TRC refill constructor here. A D constructor picks the right one, so that goes through. This one is simple. This is just showing assignment, but because we have a transitive reflexive closure here, we have to break it up, right? We have to first apply this one, which breaks it up into 2 steps, right? One for the single step and then another for the rest of the steps. This itself is direct application of the step assign constructor. So that goes through. And now these 2 states are the same, right? This one is the same as that one. So this is TRC refill that goes through. Okay. This is a bit interesting because what we are showing here is that we can take multiple steps from in C1, C2 directly go to skip, right? But the induction hypothesis sort of says C1 execute fully to skip and C2 execute fully to skip. And when you evaluate C1, you get V1. When you evaluate C2, when we get V2. The thing to note here is that we are we have unlike the earlier cases like here, right, where we right, where we applied the TRC front constructor. The thing that we actually want here is that we need a composition of um, two sequences of multiple steps, right? So this is precisely the so um, so this one, when we apply this one, the constructor that we are applying is the TRC front constructor, right? Let's probably make it more concrete. TRC front constructor, which relates a single step and multiple steps and sort of relates X and Z, right? Using multiple steps. But if you sort of stare at what the structure that we have here, we have multiple steps and then multiple steps. And we are asked to show something about from the initial state, the final state, right? So, I mean, an intuitive reading of this is if you can go from X to Y using multiple steps, and you can go from Y to Z in multiple steps, say something about how you can go from X to Z in multiple steps. We actually proved this. If you go back to your transition systems lecture, we explicitly proved this lemma, this theorem, which is that transitive flexible closure is obviously transitive. So if you can go from multiple steps from X to Y, and you can go from multiple steps from Y to Z, then you can take multiple steps from X to Z. We've proved this already. So we are going to apply that because the structure of the induction hypothesis are multiple steps. They're not single steps. So we do that, right? We actually break this up into multiple steps, right? And then we sort of say, I'm going to take multiple steps of C1, right? Multiple steps on C1. And this is what we proved with the step star seek here, right? Step star seek. In the sequence, if you can take multiple steps in C1, then you get this result. So we are going to appeal to that lemma, right? That breaks it up into what we want. So now we have a structure which sort of fits what we want. So observe that now we are sort of have this multiple steps from VC1 to some result, and we have that as part of the induction hypothesis. So this is these three steps are a little bit clever, right? So I want you to again go through these in detail. The observation is that because the induction hypotheses are broken up into multiple steps, we have to explicitly appeal to TRC trans, right? And we have to call step star seek explicitly in order to relate multiple steps of evaluations of C1 command, right? Because that is what we have in the induction hypothesis. Okay. These three steps are a little bit clever. You will encounter a similar situation in the assignment as well. All we've done is we've sort of set it up in a clear way so that we can sort of appeal to the induction hypothesis. Once you do that, everything falls right in place, right? This unifies with this one. So E assumption just plugs in the variable, and now we have skip C2, right? We know when we have skip C2, that is equivalent to just doing C2, right? And that you break it up by taking a single step. So you call the constructor here. This is applying TRC front, right? Here you apply step seek 2, right? That gets you to, that throws away that skip, right? Now you have something that matches what we have in the induction hypothesis here, right? So that actually goes through. So these few steps are actually interesting, right? So you will have to do something very similar And my recommendation is study what these are doing. You will encounter a similar situation there. Structure your lemmas in a very similar fashion, because otherwise you'll get into interesting corner cases. Right? So, but if you follow this recipe, it sort of goes through. The other ones are sort of straightforward. I don't think there is anything more interesting here, because the all of the complexity comes from the fact that the sequencing command, the step seq one, has a step in the antecedent. For example, we can just go through this, right? So, this is if then else. We just use when here, but we know that um, the condition is true, right? And if you can take multiple steps from then to skip, if you are ending up with v prime, then you end up with v prime. This is straightforward application of constructors. Okay, so um, so you can take a single step here, but we know that E is going to be true, right? So you are asked to prove E is true. Of course, assumption makes it go through, right? Then this is the same as um, the assumption here. So that goes through as well. Same for false, and actually same for the rest of the, I mean, except the while loop where you have to appeal to the same inductive, same step star seek. Rest of the things are going to be very straightforward. Yeah, I recommend you to go through the rest of the proofs. We've covered the difficult parts. The tricky parts are what lies here, but the rest of the proofs are quite simple. Okay, so that proves that one way, right? That says the big step semantics is equivalent to the small step semantics. We have to do the other direction as well, that the small step semantics is equal to the big step semantics. And the way we organize the proof is quite interesting. So because fundamentally, right, so um, small step semantics explains what happens for a single step, and then we have to extend it to all the way to the end. So the way we've structured the lemmas are interesting. I mean, you will have to structure the same thing for the assignment, but intuitively it makes sense, right? So it says, let's say the initial state is VC, right? You take a single step, you go to V prime C prime. And what you do now is, now you actually go ahead and do big step semantics from here. Take the V prime C prime, evaluate all the way to the end, right? And if it is V double prime, then you could have taken the original VC, right? You could have taken the original VC, evaluated that in big step semantics, and you will end up with the same V double prime, right? So it's sort of relating a single step of the small step semantics with the big step semantics, right? And the reason why we do this is that this step star is an inductive definition, right? So we have to sort of build it up from the ground up. So we do step first, and then what we do is we sort of relate the next thing that we do is replace step with step star. If you can take multiple steps and go from V to C, from V to C to V prime C prime, and you then take this configuration and then do big step semantics, then you can go from the original configuration, which is VC, evaluate all the way to V prime, V double prime using the big step semantics. Right? So this is sort of going one way, and finally, what we will do is we will actually say, instead of just saying C prime here, if the C prime happens to be skip, then I mean there is no other possible evaluations here. So this one just goes through trivially, and then we relate VC to V prime directly. So it's an interesting way of organizing the proof, right? We have to do one step, relate to the big step semantics. Then we do multiple steps of small step semantics, relate to the big step semantics. And we say all the way to the end. This is required because of the inductive structure of the TRC referral. Okay. The proof itself is very straightforward here. It's not even worth going through in detail. It's just very straightforward. So I recommend you to do it. There is no complexity here. It's just a direct application all we do is we induct on one, we induct on the small step structure. What does that mean? For every step that we have for small step semantics, we sort of we sort of prove this holds, right? If you can take a single step in assignment, then I can take um, then I can evaluate from that result all the way to v double prime. Then you can go from the original to the v double prime. It's mind-numbingly straightforward. So I recommend you to go through it on your own. But there is nothing happening there. Okay. But now we can actually apply that lemma in order to show that this lemma holds, where we take multiple steps of the small step semantics, and from that configuration apply big step semantics, right? Apply big step semantics from v prime c prime. And we relate it to the full evaluation. Right? Here again, we induct on one, which means we induct on the transitive reflexive closure here. So we get two sub goals, right? Which turns out very simple. It's trivial to be it's part of the custom. That's fine. Here, this is similar to what we've seen earlier, right? Just before this one, we sort of had a very similar structure. Again, this is explaining how to go from one step, then multiple step, then it relates big step semantics here. So the first thing that we did there was we set cases y, just so that Coq will actually reify the fact that this is a pair, right? We do cases y. There is a single pattern essentially, which is a pair, right? And now we appeal to the lemma that we just defined earlier, right? This is the intelligence step. So we appeal to the lemma here. So once we appeal to the lemma, we are asked to show one step of the small step semantics, for which we have a pattern here. So one step of the small step semantics, and then we have the a valuation, right, which sort of relates v double prime here, right? VC is universally quantified right here, but VC must be equal to V0 C0, right? And they are equal to V0 C0. So we are applying the induction hypothesis. We are asked to prove obvious facts, right? So this is very similar to what we had encountered earlier. And eval V prime, C prime, V double prime, that is just part of the assumption as well. This comes from this position, V prime, C prime, V double prime. Right? And that makes it go through as well. So we now related multiple steps of small step semantics, stop, take that configuration, evaluate all the way to the end, and we are relating that to the big step semantics from the start. Now that we've done that, we've done the hard work actually. So this is a specific instantiation of this one, right, where we plug in skip for C prime. So simplify it, directly appeal to this lemma that we proved, right? Apply that lemma. And the only possible assumption here is skip, right? So this unifies with skip, so that goes through, and then and this is sort of saying if you start at v prime, run skip, what is the result? It's just v prime, so that goes through as well. So what we've done here is we've related small step semantics, the result of the small step semantics, to the big step semantics. So we've done both directions, right? So both small step is related to big step is related to small step. The high level takeaway here is how we've organized the proof, right? Because the high level point is that there are multiple ways of giving semantics, and we are showing that the two ways that we've described here, the small step and big step, are equivalent for the language that we've just described. It gets a little bit more interesting, right? In the assignment, I won't probably tell you what it is now. You can have a look at the assignment, and then you will find that it has some interesting non-deterministic properties. But the proof that I will ask you to actually write, which is to relate a small step and big step, It'll be interesting because of non-determinism. You will actually say some interesting facts while relating it this way. But the proof structure organization is going to look very similar, right? That's what I want you to keep in the back of the mind. Um, of course, when you actually look at the problem, you sort of relate this to how we've done here, and the proof will go through. I promise you that it will be, you will prove more interesting properties than just saying directly they are equivalent. Because of non-determinism, we are going to say something more interesting. Anyway, so I'll stop here, and then we can catch up next Monday. Um, of course, actually, I won't ask you any questions on operational semantics in the midterm because you haven't done the assignment, so you've not probably had a chance to reason through it in any detail. So we'll skip operational semantics. We have enough material even otherwise. So we'll just have stuff on other material. So okay, so we'll stop here. We'll cover additional material on operational semantics next week, but none of that is going to be, again, none of operational semantics, none of what I teach next week is going to be part of the midterm. So, okay. So anyway, so we'll stop here and then we'll catch up on Monday. Thank you very much.